I've got something interesting to show you. I've got something interesting here that Well, that's Jim Cunningham, lives next door. You know, I think I've heard him practice on that horn of his for at least 10 years. Hi, Jim, come on in. Have you ever seen my tool shed?
No, I don't think I have. Say, these are interesting. They look a little tired, though. Maybe you've been using the wrong kind of music on them.
Well, what can you do about it?
Well, dig this, man. I'll show you. Hey, fellas, come on in.
Yeah! Flowers out of the way. Yeah, come on, let's get, come on, Jimmy.
Don't take long when you know how.
Yeah. Tub's up here. Yeah, that's the way. Why, hi-hat. Let me start it off.
This primrose plant appears to be dancing as a result of controlling the light, temperature, and moisture, and synchronizing the resulting growth responses to pre-recorded music. Hello, I'm John Ott, and I would like to show you the time-lapse greenhouse where I make time-lapse pictures of flowers growing. It is made of ultraviolet transmitting plastic that transmits the full spectrum of natural sunlight, as I have found with most plants that this is necessary in order to grow the strongest and healthiest specimens. Other factors, including nutrition and moisture, are of course also very important, as well as air, and especially humidity when it comes to growing orchids. Humidity, though, is also a problem in keeping the film in the cameras for the long periods of time necessary to photograph a growing plant. So the long plastic hoses bring conditioned air to the aluminum hoods over each camera. Time-lapse photography is just the opposite from slow-motion pictures. And here you can see a bird of paradise burst into bloom in a matter of a few seconds. In taking time-lapse pictures of plants growing, I've encountered some interesting exceptions to the general rules of nature. Photographing the growth of a banana was a very good example. Not having any bees in the greenhouse, I thought I might have to artificially pollinate the banana blossom. So I got out my little camel's hair brush, but I couldn't find any pollen. I contacted the research people at the United Fruit Company and learned all about a banana being what's called a parthenocarpic fruit. This means it produces mature fruit without the blossoms being pollinated. The banana is one of the oldest fruits to grow on this earth, and it is thought that originally it did produce pollen, but it no longer does. It is male sterile, and this is a great handicap to the banana growers because it means they cannot cross-pollinate or hybridize bananas to develop new, improved varieties. To take this picture from the emergence of the first shoot to the mature fruit required 10 cameras operating continuously day and night for 2 years. Here you see some of the additional attachments and gadgets that I borrowed from the works from the old kitchen clock that I used to make my first automatic timer. Before building the ultraviolet transmitting greenhouse, I made my time-lapse pictures in this basement studio that I called my ivory cellar. The cameras and subjects were under this skylight, which made it necessary to supplement the restricted daylight with various types of artificial light sources. Each time a single frame is exposed in any of the cameras, the supplemental growing lights are turned off momentarily, the overhead shutters closed to shut out the daylight, so I have the same amount of photographic light for an even exposure day and night and regardless of the weather. Here is a time-lapse picture speeding up the action of taking time-lapse pictures so that you can see how the cameras move forwards and backwards, they tilt up and down and pan from side to side as programmed in advance to follow the growing subjects. At normal speed, the hand cranks turn about the same speed as the hand on a clock, so this will give you an idea of approximately how much some of the action is speeded up through time-lapse photography. Here is a time-lapse picture of an iris, which is a nocturnal or night-blooming flower. This is a hibiscus, which blooms during the daytime. And here is a camellia that blooms according to a relationship between temperature and the dark nighttime period. The nights must be very cool to bring the camellia into bloom, but the temperature during the daytime is relatively unimportant. It is just the opposite, though, with the azalea, which commercial florists can force into bloom ahead of the normal season by controlling the temperature in relation to the light period. Here is a cactus that grows in the hot, arid desert. Plants as well as many animals have adapted to various environmental conditions. In contrast to the cactus, here is a water lily. This is the passion flower. And here is an orchid that requires a warm, moist atmosphere. These flowers all grew quite well without any difficulty. But the first problem that I encountered with any possible scientific significance came as the result of attempting to grow a pumpkin from the emergence of the first shoot to the mature pumpkin for Walt Disney's film, Secrets of Life. I planted some pumpkin seeds in large boxes of soil and placed them under the skylight in the ivory cellar where the young plants received some direct sunlight around noon when the sun was directly overhead, but not during the morning or afternoon as they would outdoors. So I installed some ordinary fluorescent light fixtures with cool white fluorescent tubes that are very rich in the yellow-orange part of the spectrum because of more energy in these particular wavelengths. They're designed this way to give a warmer tone to cosmetics and interior decorations. Here you see the tendrils reaching out to some solid object for support. As soon as they find something, they wrap themselves around and get a good firm grip, then start winding themselves up to form a natural spring that snubs the plant down, and they won't break so easily. The first thing that I learned about a pumpkin was that it is a monoecious type of plant, meaning that it produces the staminate and pistillate blossoms separately on the same vine. Here you see some of the staminate blossoms, extra large, healthy specimens. The leaves are nice and green right to the very tip point of each leaf, indicating no apparent nutritional deficiencies. But while all the staminate blossoms grew so nicely, I suddenly realized that all of the pistillate blossoms with their little embryo of the pumpkin right under the flower would only reach this early stage of development and then stop right there and dry up, turn black, and drop off the vine. So I didn't get any pumpkins. The second year, my lights were old and beginning to flicker. So without asking for one type of light or another, I bought some new fluorescent tubes, and the second year, all the pistillate blossoms grew very nicely, and all the staminate blossoms dried up and dropped off. This was just the opposite from the previous year. I repeated this experiment a number of times and found that I could obtain 100% staminate or pistillate blossoms on a pumpkin vine by simply supplementing the restricted daylight with either cool white or daylight white fluorescent, which I happened to be using the second year. Daylight white fluorescent is strong in the blue end of the spectrum. Chinchilla breeders are now able to obtain up to 85 or 90% male or females in the litters, depending on the lights used in the breeding rooms. Here at last is the pumpkin that was in Walt Disney's film, Secrets of Life. And here are the two types of light, side by side, next to the skylight. A large seed company asked me to make some time-lapse pictures of morning glories for one of their films, and I thought this would be a very simple project and promised the pictures in about 2 weeks. But well into the second year, they were becoming a little irritated at all the excuses I was offering as to why I could not deliver the films. The reason was the buds would reach the stage where I would expect them to open by the following morning, but instead they would simply shrivel up and collapse. This was the first commercial project undertaken in the new plastic greenhouse, so I tried it again in the old glass greenhouse, but had the same results. Then on one of my gardening television programs, I was interviewing a commercial florist who specialized in bringing chrysanthemums into bloom the year round by controlling the periodicity of the light, and also timing the blooming of poinsettias for the Christmas trade by interrupting the night dark time period with artificial light. Meanwhile, I discovered that the morning glories are a night blooming flower, so I decided to hang a light out on the garden fence where they've been blooming perfectly normally all summer. I connected it to the automatic timer in the greenhouse so it turned on for a few seconds every 5 minutes during the dark nighttime period. The next morning, within a perfect circle around the light, the buds were collapsing as they had in the greenhouse. Then I happened to run out of the regular type of film that I was using, and the only film I had available was daylight type Kodachrome. That meant changing the photographic lights to the slightly bluish ones to match the daylight film. The buds began opening just a little, which was the first encouragement I had had in almost 2 years. The only difference that I could see was in the light, so I decided to put some additional blue filters over the slightly bluish lights, and of course it made the picture very blue, but it also filtered out the red, or the longer wavelengths from the spectrum of the photographic light, interrupting the normal dark time period. By filtering out this part of the spectrum, the buds then opened perfectly normally. But the pictures were so blue, I tried placing a red filter over the camera lens to correct the color. To begin with, I had too strong a red filter, and it made the flowers look purple. So by cutting down on the strength of the red filter over the camera lens and keeping the blue filter over the lights, I was finally able to obtain a reasonable color balance photographically, but still basically filter out the red or longer wavelengths from the spectrum of the photographic lights interrupting the normal dark nighttime period. And here at last was the picture of the morning glory. This indicated that this biological response is not to the total spectrum of light interrupting the dark period, but rather a narrow band of the longer wavelengths in the red end of the spectrum. I was asked to make some time-lapse pictures of tomatoes growing for some of the old-time tomato growers in the northern Ohio area. I learned that their tomato plants seemed to be more subject to tomato virus that you see affecting this plant during and following long periods of cloudy weather in the wintertime and in their glass greenhouses. Ordinarily, this virus spreads so rapidly that on the first signs of it, they rogue the plants out and burn them. They happen to have several plants growing in their experimental greenhouse just beginning to show this virus condition, and they were very happy to have me take them home with me from their glass greenhouse to my ultraviolet transmitting plastic greenhouse that lets through a more complete spectrum of the full natural sunlight. I continued to use the same fertilizer program that they were using, and not only the plant being photographed, but all 6 of the plants I brought back perked right up, started putting forth healthy, vigorous growth. They set buds and produced tomatoes, which was considered unheard of and impossible according to the old-time tomato growers. The process of photosynthesis is sometimes described as being a conversion of light energy into chemical energy, and viruses are often referred to as being an abnormal chemical or an abnormal chemical compound within the cell. Accordingly, I believe that these pictures and others that I've taken strongly suggest the possible relationship between the abnormal chemistry associated with viruses responding through this process of photosynthesis to an incomplete or unbalanced light energy source, and that there may be a very direct relationship between viruses and light energy that should be further studied. Here you see the tomato developing, and as you watch, you will see it turn a nice red color as it ripens. It is interesting how different species of plants respond to different light conditions. A tomato can be picked green from the vine and placed on a shelf in a dark closet, and it will develop a red color. Whereas an apple left growing on the tree would not develop a red color until a glass skylight was removed and replaced with ultraviolet transmitting plastic, indicating that the ripening of an apple is dependent on the ultraviolet wavelengths that do not penetrate ordinary window glass. Here you see the streaming of the chloroplasts within the cells of Elodea grass. I have found that under full natural sunlight, all of these little chloroplasts get into a streaming pattern and go in an orderly fashion around and around to each end of the cell. But if the light is filtered through ordinary glass that cuts out the ultraviolet, or, as in this case, an ordinary incandescent microscope light source lacking the ultraviolet was used, many of the chloroplasts drop out of the streaming pattern and form a sluggish clump in one part of the cell or another. When I placed a red filter in the light source, restricting the wavelengths to just the longer ones that we see as red, some of the chloroplasts responded in their normal pattern, some dropped out of the streaming altogether, and others started shortcutting across without going all the way to the end of the cell. This would appear to be affecting the normal process of photosynthesis and the resulting cell chemistry. I then decided to change the red filter and insert a blue one, letting through the shorter wavelengths. And as you can see, some of the chloroplasts continue to respond normally, some have dropped out altogether, but those shortcutting go down to the upper corner before they make their shortcut. I removed the color filters and added a very low level of long wavelength ultraviolet or black light to the ordinary incandescent microscope light source to come as close as possible, in a crude way, to the full natural spectrum of sunlight. And you see just about all of the chloroplasts resuming their normal streaming pattern. At the end of the day, no matter how much I would increase the light intensity, the chloroplasts would just run down like a dead battery and refuse to respond any further until they had had their normal dark night rest period. This points up the importance of the seasonal changes in the length of day and darkness, or what is commonly referred to as the periodicity of light. Chrysanthemums normally bloom in the fall of the year as the length of daylight gradually shortens and the dark nighttime period increases. Many florists take advantage of this biological phenomenon and force their chrysanthemums into bloom ahead of the normal season by artificially shortening the long daylight hours They cover their plants with black cloth about 4:30 in the afternoon and keep them covered for several hours after sunrise the following morning. Blooming can be delayed by turning lights on and artificially lengthening the short daylight periods of fall and winter. This is how florists control the blooming of chrysanthemums so that they are available every month of the year. The blooming of poinsettias is also controlled by light, so they will reach their peak of bloom just in time for Christmas. In the early 1920s, a Canadian zoologist by the name of William Rowan discovered that the migration of birds is also controlled by the seasonal changes of the length of the day and night periods. The poultry industry has learned that egg production can be increased by lengthening the daytime periods with artificial light, and especially during the short daylight hours of the winter. More recent research by a number of scientists has indicated that light entering the eyes influences the pituitary and pineal glands by means of neurochemical channels that are independent of the optic nerve. These master glands control the entire endocrine system and the resulting basic body chemistry through the production and release of hormones. Thus, it appears that the conversion of light energy into chemical energy through the process of photosynthesis in plants carries on into animal life in a much more improved and more sophisticated way. Here is a pigment epithelial cell from the retina of a rabbit's eye, as seen through a microscope. These cells are located right behind the rods and cones, but are thought to have no visibility function. These pictures were made in connection with a drug toxicity test to see what the effects of various tranquilizing drugs might be that were known to cause various side effects. I very quickly found that the color of the filter used in the light source of the microscope to increase the contrast of the pictures photographically had a far greater effect on the cells than the drugs being tested. With the blue filter, the cells seem to go through all sorts of contortions, as you see here. With the red filter, the response was entirely different, an apparent weakening in the cell walls or the cell membrane, which would rupture, allowing the cytoplasm or the contents to run out and, of course, killing the cells. I used a water cooling condenser and a heat-absorbing filter, so I'm certain it was not a matter of a difference of temperature. Whenever a color filter was used more than a few hours, there would be no more normal cell division or mitosis. This raises the question of what effect colored filters like sunglasses may have when placed in front of the eyes. Even without a color filter, but using an ordinary incandescent light source, in a matter of a few days, the pigment granules would become sluggish and there would be no further mitosis or cell division. The punch mark in the film indicates I've added a small amount of long wavelength ultraviolet light, same as I did with the chloroplasts, and then the sluggishness of the pigment granules would be broken up and the cells would continue their normal cell division process. Here again, you see the cells in their normal state, and the second punch mark indicates a higher intensity of ultraviolet, and immediately you begin to notice a very abnormal response, and finally, a rupturing of the cell membrane. This is from too much ultraviolet. These same cells appear to be more active in the morning and gradually slow down toward evening. They too must have a dark period just like the chloroplasts in the cells of a leaf. Then the following morning, they are more responsive to light energy. Here are heart cells from a chick embryo, and again with a blue filter, you notice a complete change in their appearance and metabolic rate of activity. After seeing these pictures, several well-known virologists have commented that this reaction resembles very closely cells being attacked by viruses. They could hardly believe me when I explained that I could consistently repeat these responses by simply placing a blue filter in the light source of the microscope. This is another possible indication of a relationship between viruses and light energy. With a red filter, again an apparent rupturing of the cell membrane, allowing the cytoplasm to run out and killing the cells. These pictures show similar growth responses in animal cells to different wavelengths or colors of light that might otherwise be more closely associated only with plant cells. After noting the effects of different colors or wavelengths of light on plants, I thought it'd be interesting to experiment with different types of lights on laboratory animals. In the upper two tiers of this compartment are some of the deeper colors, while in the lower two tiers are some of the different types of fluorescent lights commonly used for ordinary lighting purposes, such as cool white, warm white, daylight white, and others, all of which represent gross variations or distortions from the spectral distribution of natural outdoor daylight. Some of the laboratory animals were kept in this large compartment outside in the natural daylight. The three openings to the right have ordinary window glass that stops most of the ultraviolet. The next three openings to the left have ultraviolet transmitting plastic, and the next openings have a synthetic type quartz glass that will transmit further into the shorter wavelengths of ultraviolet. The three openings to the extreme left are equipped with an air curtain, that is, just a screening to keep the insects out. The air is exhausted from the center of the animal room indoors through all these various compartments and out the three on the left. So none of the animals in this outdoor compartment are receiving any more fresh air than those kept indoors. This is where the microscopic time-lapse pictures are made. The first significant response to the different lighting conditions was noted in the tails of the C38 strain of mice, which are extremely susceptible to spontaneous tumor development. When housed under pink fluorescent 14 hours a day for 3 months, the tails became spotted and severe lesions occurred, causing the abrupt curling at the end. The tails of the animals receiving the natural daylight through the air curtain device remained perfectly normal. At the end of a 3-month period, some of the animals were transferred from the pink fluorescent to the air curtain compartment, and after 30 days, the condition of the tails became perfectly normal. The animals remaining under the pink fluorescent light for 6 months developed a condition of complete necrosis, or, in other words, lost their tails. When this same strain of mice are kept under the relatively new type of purple light developed for growing plants, they lose most of their fur at the end of 3 months. There are many other sores that develop, and the tail becomes very scaly, but does not actually drop off as it does under the pink fluorescent. 6 months under this purple plant growth light produces a pretty unhealthy looking animal. The tails and fur, of course, are exposed directly to the light, but here is heart tissue which is not. This is very strong, healthy tissue, and is typical of that found as a result of autopsies performed on all of the animals that have been in the air curtain compartment, which received natural daylight. The small dark spots are the nuclei of the cells that absorb the stain used in preparing the slides. Here, however, you see large dark areas which are calcium deposits known as calcific myocarditis, and this condition was typical in all of the animals from the pink fluorescent compartment. Here is the owner and operator of one of the largest mink ranches in the country. In breeding mink, it is a common practice to inject the females with the pregnant mare serum if they do not become pregnant after mating. The results of this experiment indicated that behind the blue plastic, all of the females became pregnant after their first mating, and all of the males were classified, as known in the trade, as working males. Furthermore, both males and females became very friendly and docile after 90 days behind the blue plastic. Behind the pink plastic, and after 3 attempts at mating the females and injecting the pregnant mare serum, only 86% became pregnant, and 90% of the males were classified as non-working males. These animals behind pink plastic also became noticeably more aggressive and more difficult to manage. Former Warden Reagan of Stateville Penitentiary in Illinois was a great believer in horticultural therapy. He was a guest on my TV gardening program on several occasions to tell of the work done by the inmates of the penitentiary. I also visited him on several occasions and was amazed by the beautiful gardens within the prison walls and also the very extensive prison farms. Warden Reagan stated on many occasions that it was only through horticultural therapy that he was able to rehabilitate some of the most extreme psychological cases, making them actually eligible for parole. He said that other forms of manual therapy, including painting and sculpture, done indoors did not have the same beneficial effects. Maybe the results of the horticultural therapy were purely psychological in getting the men closer to nature and working with flowers. And maybe getting them outdoors into the natural sunlight may have been a very important factor, especially when consideration is given to how poorly the average jail cell is lighted. After noting how adding a little long-wave ultraviolet to the incandescent light of the microscope made just about all of the chloroplasts get back into their full streaming pattern, I decided to experiment in adding some of these same ultraviolet wavelengths to the laboratory animal compartments. But I had no way of measuring how much ultraviolet was actually reaching the cells in the microscope slides. While I was thinking about this project, I happened to have dinner in the restaurant known as the Well of the Sea in the basement of the old Hotel Sherman in Chicago. The first thing that caught my attention were the blacklight ultraviolet lights placed in the ceiling and in the alcoves. This was the same type of long-wave ultraviolet light that I had used in my microscope experiments. It was installed in the restaurant purely for decorative and ornamental purposes. I asked the captain how long the lights had been installed and whether he had noted any harmful effects as far as the men working for him were concerned. That is, had the men developed any skin cancer, cataracts, or other problems commonly associated with exposure to ultraviolet? He advised that the lights had been installed for over 20 years, that essentially the same group of men were still working there, and that their health record had been so unusually good that the manager of the hotel, under medical supervision, had been investigating this situation to try to determine why this particular group of men always were on the job, even during some of the most severe flu epidemics, and also why they seemed to be so unusually congenial and efficient in their work. Shortly thereafter, I visited the Miami Seaquarium, and I noticed one area where ultraviolet blacklight fluorescent tubes had been placed over some of the aquariums. I asked the director about this, and he explained that in view of the increasing interest in psychedelic lighting, this was done just to create an eerie effect. He went on, though, to state that he had noticed within 10 days after installing the blacklight ultraviolet fluorescent tubes a severe condition of papae, or exothalamus, in some of the fish completely disappeared. He and his co-workers also noted that this added small amount of ultraviolet eliminated another very common problem, that of fin nipping. He also mentioned that he was now able to keep many rare species of fish thriving that never could be kept in captivity before. We have experimented in breeding rats under standard cool white fluorescent and the new full spectrum type of fluorescent tube. Under ordinary types of fluorescent light, it has been common practice to remove the male from the cage before the litter arrives because of the tendency toward cannibalism. However, under the new type of fluorescent tubes, it is no longer necessary to remove the male, as he invariably will show a more normal parental instinct in helping to take care of the young. Here at the State of Florida Marine Research Laboratory, I have been very fortunate in having the opportunity of serving as a consultant. A new laboratory building has been constructed using ultraviolet transmitting plastic in all of the skylights and windows, as well as the new type of full spectrum fluorescent tube for all of the artificial lighting. Here is Dr. Frank Hoff on the right, who with his assistant are both working on a project to find a way to raise shrimp on a commercial farming basis, as has been done in the past with catfish. In the old laboratory under standard cool white fluorescent lights, the chief problem encountered was that of cannibalism. In the new laboratory under the ultraviolet transmitting plastic and the full spectrum fluorescent tubes, which are very seldom used, this problem of cannibalism has disappeared. Here is the St. John Brebeuf School in Niles, Illinois, a suburb of Chicago. In 1963, the Communicable Disease Center of the U.S. Public Health Service in Atlanta reported an unusually high rate of leukemia with the children attending this school, the highest rate of any school in the country, 5 times the national average. Many of the national cancer agencies, both public and private, have investigated this situation, but no positive explanation for this unusually high rate of leukemia has been found. And until an explanation is available, I believe that every possible clue should be explored. With this in mind, I visited the school and learned some interesting bits of information not previously uncovered. All but one of the leukemia cases were in 2 classrooms where the teachers followed the practice of keeping the curtains closed at all times because of the glare from the large areas of glass used in constructing the building. This then meant keeping the high-intensity fluorescent lights on continuously, which at the time of the high leukemia incidence happened to be the deluxe warm white fluorescent tube, which is the pinkest of any of the standard tubes used for ordinary lighting purposes. In checking all the available records, I learned that this leukemia cluster, as this type of situation is commonly referred to, developed shortly after the teachers in these two rooms were transferred to this school and started to keep the curtains closed regardless of the weather and the fluorescent lights turned on all the time. I further learned that this situation had disappeared shortly after these same teachers were transferred on to other schools. And coincidentally, at this same time, all of the deluxe warm white tubes were old and were replaced with cool white, which, though not a full spectrum type of tube, do represent less distortion than the deluxe warm white when compared to natural sunlight. The possible significance of this may be better illustrated in this chart, showing the influence of wavelengths of light on tumor development in C3H mice. Here is the visible color spectrum, starting with the longer wavelengths, which we see as red, on through the various colors to the shortest visible wavelengths of violet, and beyond the range of human vision into the ultraviolet, then X-rays, gamma rays, and cosmic rays. Into the longer wavelengths come infrared, radar, television, and radio broadcasting wavelengths. This deep yellow line represents sunlight energy, as measured by the Bureau of Standards in Washington, D.C. The intensity is fairly even through the visible portion of the spectrum, peaking a little in the blue-green, but then cutting off abruptly in the ultraviolet at approximately 2,900 angstroms because of the filtering effect of the atmosphere. The Bureau of Standards and other similar charts show an absolute cutoff at this point, but I'm continuing this line at the very bottom of the chart because it is now recognized by many physicists that trace amounts of these shorter wavelengths do penetrate the atmosphere to the surface of the Earth. This pink line represents the spectral energy from standard pink fluorescent tubes. Under this narrow part of the spectrum, these mice developed tumors and died within the average lifespan of only 7.5 months. Under the broader spectrum from daylight white fluorescent, the lifespan increased to an average of 8.2 months. Ordinary single-strength window glass comes closer to the full spectrum of natural sunlight, but does cut off in the ultraviolet spectrum at about 3,300 angstroms, and the lifespan goes up to 9.4 months. Some eyeglasses are designed to cut out all of the ultraviolet at about 3,800 angstroms. The biggest increase in the lifespan is noted in the animals under the full spectrum of ultraviolet transmitting plastic that cuts off virtually at the same point as the atmosphere, around 2,900 angstroms, and the animals lived for an average of 15.6 months. Under the synthetic type quartz glass, there is a cutoff in the ultraviolet around 2,300 angstroms, and the lifespan goes up just a little more to 15.8 months. Under the full spectrum of natural sunlight received through the air curtain, the lifespan increases to 16 1/10 months, which is more than double the lifespan under this narrow part of the spectrum alone. On first thought, one might conclude that these wavelengths are harmful, but actually they are part of the total spectrum. So it is then suggested that the faster tumor development and other abnormal growth responses are not caused by the presence of these waves, but rather by the absence of the wavelengths that are missing. This condition of malnutrition might be compared to malnutrition that results primarily from what is lacking in a proper diet. Experiments at 6 medical centers have revealed similar positive results of the effects of light on tumor development. We have seen how the morning glories were affected by the longer visible wavelengths that we see as red, and how an apple refused to ripen under ordinary window glass that stops the transmission of ultraviolet. But this flower, the night-blooming cereus, which is a nocturnal flower, opens quite normally regardless of the intense photographic lights flashing on and off during the dark nighttime period. When I placed the night-blooming cereus and this day-blooming cactus side by side in a dark closet, the night-blooming cereus would not open until it was dark outside, and the day-blooming cactus would wait until it was light outside before it would open. It would close up each night and open the following day regardless of the incandescent photographic lights. This type of response is generally referred to as a circadian rhythm, which is thought to be controlled by some sort of built-in biological clock. It occurred to me that these responses might be to wavelengths of the total electromagnetic spectrum Beyond those of visible or ultraviolet light, such as X-rays, cosmic rays, or even some of the longer wavelengths that are capable of penetrating ordinary building material as readily as visible light penetrates window glass. Here is another example, the Hoya vine or wax plant, which is also a nocturnal flower. The blossoms open part way the first night, remain perfectly motionless during the ensuing day, and then open the rest of the way the next night, even though it was kept in a dark closet. Here is another very interesting plant, the Mimosa pudica, or sensitive plant, and through time-lapse photography you can see how its leaves close each night as the plant literally seems to go to sleep. If you strike the leaf with your finger or other solid object, the leaf quickly closes as seen in this normal speed picture. If the leaf is singed with the flame of a match, the shock is greater, and the little leaves not only fold up, but the individual branches or petioles collapse and droop downwards. The shock is then transmitted throughout the entire plant to the other little branches, which first collapse, and then to the individual petals, which fold together. If some ordinary ether is poured on cotton and placed near the plant, and it is covered with an airtight cover such as this box with a glass front, the reactions of the plant become very slow and sluggish within approximately 5 minutes. In another minute or two, there is still less reaction, and in approximately 8 or 9 minutes, the plant becomes completely anesthetized and shows no response at all. However, after it remains in the open, fresh air for another 10 minutes or so, it again reacts in its normal way. If this plant is placed in a dark closet near the surface of the earth at noon, the leaves remain in their daytime position until the sun sets and it becomes dark outdoors. Then the leaves close for the night. To find out what the response of the leaves might be to any wavelengths beyond the range of visible light, but capable of penetrating ordinary building material, an experiment was undertaken. I selected several plants and took them down to the bottom of a coal mine 650 feet below the surface of the earth. This massive amount of earth is very efficient in shielding the so-called general background radiation. At the bottom of the mine, all the sensitive plants immediately assume their nighttime position, not waiting for the sun to set, as the plant did in the dark closet at the Earth's surface. This experiment therefore suggests that at least some biological rhythms in plants, and possibly even animals, may be direct responses to wavelengths within the total electromagnetic spectrum, but beyond the range of visible light, that are capable of penetrating the building material surrounding the closet at the surface of the earth, but not the massive amount of earth at the bottom of the coal mine 650 feet down. Here's another interesting plant, the Venus flytrap. It has a built-in mechanism more like a digital computer with a built-in memory bank. On each flat surface of the trap are 3 hair-like triggers. This plant can count up to 2. It is necessary to touch any one trigger twice or any 2 triggers each once within a given length of time. Then, bingo, the trap shuts fast enough to catch a fly. In 1964, a paper was presented at the American Academy of Pediatrics meeting in New York City, mentioning a number of abnormal symptoms in young children referred to as the tired child syndrome. The severity of these symptoms seemed to be directly related to the amount of time the individual children spent watching television. These abnormal conditions were thought to be caused by an over-psychological stimulation resulting from the program content, that is, too many Western thrillers and murder mysteries. However, suspecting that X-rays from the TV sets might also be a possible contributing factor, I placed some bean plants in front of a TV 6 hours each weekday and 10 hours on Saturdays and Sundays, the same amount of time that the children were watching their TV sets. The bean plants on the right were protected with a solid lead shield that would stop X-rays and showed the same amount of growth as control plants placed at a distance of 50 feet. The bean plants on the left were shielded only with black photographic paper that would stop all visible light but would have no effect on the X-rays. You see an extremely stimulated growth with the leaves 2.5 or 3 times the size of the lead-shielded plants. The plants near the top or above the TV set showed the roots emerging from the soil, whereas the roots of the plants near the bottom or below the TV set followed their normal downward growth pattern. This has some very far-reaching implications, indicating that gravity may not be the controlling factor in the downward growth of the roots of plants, but that they may be growing away from the general background radiation that normally comes only from overhead because of the shielding effect of the massive amount of earth beneath. Next, I place some young white rats directly in front of the TV set with the same time periods as both the bean plants and the children exhibiting the tired child syndrome symptoms. Through semi-time-lapse photography, partially speeding up the action, you can see that the young rats on the left, protected only with the black photographic paper, became aggressive and more difficult to manage, whereas those on the right, protected with the lead shield, remained perfectly normal and docile. Autopsies were performed on all of these animals, which showed brain tissue damage in those protected only with the black paper, but not in those protected with the lead shielding. In another experiment, it was found that all of the TV sets in the homes of a group of hyperactive children being sent to a special adjustive educational center were giving off various amounts of X-rays, and when these sets were repaired or discarded, all of the children within a period of only a few months showed sufficient improvement so that they could be returned to their regular classes. In 1968, I was asked by Paramount Pictures to make the time-lapse sequences of geraniums and other flowers for a film on a clear day featuring Barbra Streisand. I found that the geraniums would grow very well indoors under the new type full-spectrum fluorescent tubes that more closely duplicate natural sunlight. However, they seem to grow noticeably better near the center of the tubes than at the ends where the cathodes are located. After I had finished all of the pictures for On a Clear Day, I placed two of the large fluorescent fixtures, each holding 10 8-foot tubes, outdoors, end to end. Bean seeds planted in pots placed near this concentration of the cathodes showed a stunted, distorted growth compared to the seeds planted in pots and placed near the center of the tubes. Here you see the difference in the growth responses. When the pots were protected with a lead shield, the bean seeds grew normally. However, when they were protected with an aluminum shield, the bean seeds continued to show the same type of stunted and distorted growth. This suggests a low level or trace amount of X-rays, even though none could be detected with conventional X-ray measuring equipment. When I placed bean seeds on wet cotton near the concentration of all these cathodes, the shoots showed a random directional growth, some turning upwards, some sidewards, and a few downwards. But when I shielded the seeds with lead foil, all the shoots followed their normal downward directional growth. In another experiment, time-lapse cameras were used in a standard first-grade classroom, and several hyperactive children may be noted, especially the boy in the immediate foreground. "90 days after, the regular cool white fluorescent tubes were replaced with the new type full spectrum fluorescent tubes with radiation shields, there was a marked improvement noted, and the extremely hyperactive boy has voluntarily moved up to the front row. He raises his hand for recognition and is now up at the blackboard taking part in classroom activities. Prior to the time that this new lighting was installed, this particular boy had an extreme learning disability problem, but quickly learned to read within 90 days after the new lights were installed. There was further noted a general average improvement in both the behavior and academic achievement of the entire class. There are, however, other factors that must also be considered. The implications of the biological effects of light and radiation as observed through time-lapse photography are obvious. I sincerely hope that what started strictly as a hobby and intended only for entertainment purposes may help stimulate further greatly needed scientific studies in this very important area of research." This is a petri dish of Physarum polycephalum, a slime mold that makes an ideal organism for cellular research. Ordinarily, it grows on decaying wood out in the forest, but growing it in the laboratory is a different matter. First, a plasma is made and put in jars that are shaken in this machine so that it is thoroughly mixed. Now a small amount is placed on some absorbent paper in the Petri dish, and a nutritive solution is added. Here in time-lapse photography, you see the growth taking place as it spreads out over the absorbent paper. Here is a close-up, and you can see the actual slime mold beginning to grow. It spreads out with these fan-like protrusions in all directions. Normally, the spores are carried by the wind to other locations, but here in the laboratory, Physarum polycephalum will just keep on growing in one location. Here is a microscopic picture showing streaming of the protoplasm. Dr. Harold Rush and his colleagues at the McCardle Laboratory at the University of Wisconsin found that in order to make it sporulate, it had to be placed in this light chamber for a matter of about 4 hours. This light treatment causes the spore heads to form, and then they grow larger and larger. And here you see this pulsing type growth through time-lapse photography. It cannot be seen at normal speed, and it just keeps on growing like this. A group of researchers at the University of Minnesota tried to grow Physarum polycephalum in their laboratory and were unable to make it sporulate, even though they very carefully followed the protocol established by Dr. Rush and his colleagues at the University of Wisconsin. They made a similar light chamber in the same number and size of fluorescent tubes, but the Physarum polycephalum would not sporulate. That is, until they discovered cool white fluorescent tubes were used at the University of Wisconsin, and they had used warm white tubes at the University of Minnesota. Cool white has more energy in the yellow-green wavelengths, and warm white has more energy in the orange-pink. This emphasizes that different biological responses react to specific wavelengths of light energy. And then it quiets down, and the spore heads begin to mature and turn a darker color. It's really dark now, fully matured and ready to burst open and release the spores. Light is not the only factor affecting growth. Here is one of the county agents in Kansas, showing a comparison of good wheat grown on one side of a highway with some very poor wheat growing on the other side of the same highway. Both fields were planted with the same seed by the same farmer at the same time, but the wheat from the good field had crop rotation and fertilization. They both had the same amount of natural sunlight. The unfertilized wheat is stunted in growth and seriously infected with disease. Here is a gardenia plant, and notice how yellow and sickly looking the leaves are. This is usually due to a lack of iron, but fertilizer containing ordinary sulfate of iron didn't do any good. When I gave it chelated iron, watch what happened. It started new, healthy, vigorous green growth. The pulsing up and down motion is the result of the day and night period. With chelated iron, it just takes on new life, puts forth more green leaves, and now watch the buds develop. The advantages of natural fertilizer compared with chemical fertilizer has always been a very controversial subject. Here you see chemical fertilizer being applied. And now, the natural organic fertilizer. Here is soil in a box with a glass front. It is divided into 3 sections. The center section is plain soil, and the arrow points to a corn seed. On the left, a popular chemical fertilizer has been added to the soil. You can see a spot of full-strength chemical fertilizer. On the right, organic fertilizer has been added, and you can see a dark spot of full-strength organic fertilizer. As the soil is watered evenly across the top, you'll notice that it penetrates down a little faster on the left side with the chemical fertilizer. The organic fertilizer absorbs more moisture and is a little slower in penetrating down to the deeper depths. We're going to watch and see if there's any difference in the growth of the roots from the same seed. Plain soil is in the center, chemical fertilizer on the left, organic fertilizer on the right. Here's a close-up of the seed, and you'll notice the roots starting downward and the shoot going upward. In this particular picture, all the roots seem to go a little to the left, but they go right on by the spot of full-strength chemical fertilizer. There's no tendency to turn toward it or away from it. Over on the right-hand side, you see how the roots have developed and gone right through the organic fertilizer. But there's no noticeable turn toward either fertilizer, and the roots will go right through the full-strength chemical fertilizer. The conclusion is fertilizer does not alter the pattern of root growth. Other pictures I have taken show that roots do not turn toward water or moisture in the soil either. This is a soil test to show the bacteria in the soil and that fertilizer can be applied in the fall of the year, when working conditions are usually better and the ground is not so muddy. I brought some fertilized soil into the laboratory and made up a slide, here being placed in the microscope with the time-lapse equipment. And through time-lapse photography, you can see the bacterial activity that's in the soil. Then, as the soil temperature diminishes during the wintertime, you see all this activity just comes to a standstill as everything freezes solid. Covered by the snow, during the wintertime, it's locked in the ground. In the spring of the year, when the soil temperature rises and reaches just the right temperature, there are all of a sudden numerous little explosions of soil area, as one after another of these colonies burst, releasing the bacteria throughout the soil. Under a high-powered microscope, you can see what each of those little white specks look like. Here is another experiment showing the importance of temperature. An X-ray picture of a spot of TB on the lung, which might be compared to a black spot on a rose leaf. Here is a rose plant. Notice the leaf on the upper right-hand corner has 2 little scars where it was scratched and where black spot spores were applied. Through time-lapse photography, you can see the rosebud open. Dr. O.J. Eigsty, a biologist from the University of Nebraska, was helping me with this project. Through the microscope, you see some black spot spores. We worked for weeks trying to make the spores germinate, but with no success. Finally, he had to go back to the university when fall classes started. So we made 12 slides, placed one in each microscope to take time-lapse pictures, and put the remaining 10 in a refrigerator to hold growth back until I could get to them, one a day in each microscope. The 2 that were put immediately into the microscope remained perfectly dormant. No growth developed at all. but those placed in the refrigerator with the thought of holding them back all germinated and grew very nicely. Temperature is also a factor in the insect world. Here you see a caterpillar as it starts to spin a cocoon. And now, in the spring of the year, when things warm up, the caterpillar has changed to a butterfly that works its way out of the cocoon. We'll watch it now as it works a leg out and finally can get hold of the branch and pull itself out. You can see its wings beginning to stretch as it exercises them. The cocoon, or chrysalis, is not solely for the purpose of self-preservation during the wintertime. It is obvious that some insects must be chilled before they will complete the pupa stage. It is known that many moths and butterflies will not emerge from cocoon or chrysalis if brought into the house too early in the fall. It is thought that the reason is they dry out if kept indoors too long. In discussing this with several just plain good old-fashioned nature teachers, I am told that if cocoons are placed in the refrigerator for a while, when brought indoors early in the fall, there is no problem about their drying out. The butterflies and moths will emerge perfectly. Early in the summer of 1948, Northwestern University Medical School was interested in a project of time-lapse studies of the growth and division of cancer cells. Tissue culture slides were prepared from rat tumors. Dozens and dozens of slides were prepared and carefully transported in heated thermos jugs, but not a single picture showed any cell division taking place. Serious consideration was being given to the question of how much longer it was worthwhile to carry this project further. Then one day, the intern, who was transporting the heated thermos jug in the back of the car, carelessly allowed the cover to jiggle loose and come off. The slides were cold on arrival, and we felt they obviously had been completely ruined. But I put them in the microscopes anyway and started the cameras going. The chromosomes within the cell lined up and split in two as the cancer cell actually divided. It was hard to realize that after all these months of work, the picture of cell division happened on a slide that through carelessness had been chilled so that we considered it hardly worth photographing at all. This was the first slide that showed any cell division. Here you see a time-lapse picture showing the fungus that develops in the nasal discharge of a person with an ordinary head cold. You can see the fungus growing in the spore heads as they develop. A little branch is growing downward. Watch the end of it. A new spore head is developing there. When the spore head breaks open, the spores will carry the fungus to other locations. As the fungus grows, these cells also appear in the nasal discharge. This activity cannot be seen except through time-lapse photography. The same type of active white blood cells appear to be nature's way of fighting the fungus growth. A different type of fungus growth appears in the nasal discharge of people who have deep chest colds and laryngitis. But again, the same type of active cells appear to also fight this fungus growth. Now I'm going to show you some pictures of pollen. I will take an ordinary slide with a stigma from one blossom and some pollen from another. Then I add a media to stimulate active growth and cover it over with an ordinary cover slip. Normally I would seal this with Vaseline, but just to save time, I'll look at it through the microscope to see if there's anything of interest. If it does look good, I'll take it over to the microscope cabinet with the time-lapse cameras, put it in position, test the exposure with an electronic exposure meter, and then close everything up and start the time-lapse cameras. Finally, I'll put the cover on so that it acts as an incubator to keep everything at the proper temperature. Now here you can see through the microscope a stigma with a grain of pollen, but there's no activity because this stigma is dead. Just no activity at all, even through time-lapse photography. But here is a living stigma, and you can see the microscopic chemical particles that penetrate right through the outer membrane of the grain of pollen, activating the inner contents or protoplasm. Here is a pollen tube growing. It penetrates the surface of the stigma, and then through the pollen tube flows the protoplasm from the grain of pollen into the stigma, which in this case is a corn silk that may be anywhere up to approximately 1 foot in length. Each kernel on the cob has its own single silk, and all together they form the tassel. Each silk must be pollinated individually for all the kernels to fully develop. Here is a grain of pollen in a slide that was drying up, so I added a drop of distilled water. The additional water and capillary pressure caused the grain of pollen to quickly burst open, and again through time-lapse photography you can see the contents are very active. In this picture you can see a light flare that was caused by the microscope light not being properly adjusted. Photographically speaking, it is a very poor picture, but watch what happens. Could the increased intensity of any particular wavelength be in any way responsible for the increasing activity of this cell as seen through time-lapse photography? However, also note the little droplets of fluid forming on the grain of pollen to the right of the very active cell. I will explain more about this later. Here is another grain of pollen, ragweed pollen, and you can see little droplets forming. This is in the nasal secretion of a person who's ordinarily subject to hay fever, and the chemical reaction with the individual's particular body chemistry appears to be just what's necessary to activate the grains of pollen and cause them to give off these little droplets of fluid. These, in turn, may be what causes the irritation, rather than contact with the outer shell of the grain of pollen itself. Here are several grains of pollen. Normally a pollen tube will grow straight outward from the eye of each grain. The one you see in the center of this picture just happened to be in line toward the stigma and grows straight to it. However, note that the grain of pollen on the upper right part of this picture starts out growing toward the upper right corner, but watch how it turns in a wide arc and also grows toward the stigma. Here is another picture of a grain of pollen right on the stigma and actually making contact with it. You can see the pollen tube starting to grow upward. The pollen tube immediately makes a very sharp turn completely around and back toward the stigma. The question is, what makes pollen tubes change their direction of growth toward the stigma when the roots of plants do not alter the direction of their growth toward either fertilizer or moisture? This picture shows some aphids on the leaf of an orange tree shortly after radar equipment was installed at a nearby airport a number of years ago. I noticed that every few seconds all the aphids would tense up in unison and do sort of a little dance, as you see in the picture. Upon further investigation, I found that the interval of time between the activity of each dance coincided exactly with the rotation of the radar rotor device at the airport, which was a distance of approximately 14 miles. While this distance is vastly greater than the total area of the microscopic picture of the pollen tubes, it is nothing compared to that involved in communicating with satellites traveling to the Moon, Mars, Jupiter, and beyond. Here is a time-lapse picture of the coils of a tungsten filament taken over the full burning life of an ordinary incandescent light bulb. The surface of the metal in the coils is very smooth when it is new, but begins to crinkle and get rough from the extreme heat as the light bulb is used. These rough spots can act as point emitters and give off radiation in addition to the normal output of visible light. One of the major light bulb manufacturing companies has published in its literature to dealers that it uses extreme care in its manufacturing processes to make certain that the surface of the filaments will be perfectly smooth, so this will not happen. However, no matter how smooth the surface of the filament of a new bulb, this picture shows how the heat from the normal usage of the bulb will produce this crinkling and crackling over the normal lifetime of the light bulb. This is a sporocarp that grows on an aquatic plant known as the Miscellany quadrifolia, or cloverleaf fern. The sporocarp drops into the water, swells and bursts open, releasing true egg masses. A gelatin material dissolves, releasing a few eggs at a time. Here you see them drifting away from the general mass of the egg clusters. This is a sperm case, as seen through a high-powered microscope. It also bursts open in the water, releasing the sperms that begin to get up their own power and swim directly toward the egg. And here you see a dish-type antenna right at the end of the egg that attracts the sperms. They make contact and then go into reverse and back away. Here you see a group of sperms all fighting for position to make contact with this radar-like antenna dish. Clumping of the red blood cells in the vascular system has long been considered a major problem by many scientists. Such clumping blocks the flow of blood in the very small capillaries, where oxygen and nutritive material in the blood pass into the body tissues, and carbon dioxide and waste matter are absorbed into the bloodstream. This microscope slide shows clumping of red cells in human blood into long chains after 5 minutes of exposing the blood directly in front of a video display terminal, model Ikegami EM125A. After 5 minutes of exposing the blood directly in front of an ultraviolet light source of radiation-shielded full-spectrum Ott light fluorescent fixture, model 2020, and using dark field microscopy, the long chains of red cells in the man's blood break up. These pictures were taken using a phase contrast microscope with an orange-red filter in the light source. They are part of a research project originally intended to study the effect of adding various tranquilizers into the growth media of tissue cultures of the pigment epithelial cells in the retina of a rabbit's eye. However, the study revealed that the color or wavelength of the microscope light source caused greater side effects and abnormal growth responses than the tranquilizing drugs being tested. More information is presented on this subject in the article entitled Color and Light, Their Effects on Plants, Animals, and People, published in the International Journal of Biosocial Research, volumes 7 through 10, that are recommended as a study guide in connection with this film. Specific mention is made of the research work by Dr. Peter Langerhans, with reference to the fact that he found it necessary to use a gold-colored stain in order to see the cells that now bear his name. The article also gives similar information regarding Professor Kim Bong-han in reporting that he had to use an orange-colored stain in order to see cells which he refers to as Bong-han corpuscles. The fact that the activity you see in these pictures happened to show up like this when I used an orange-red filter in the light source may be of particular interest. When I used a blue filter, you can see a similar but slightly different activity in what also appears to be a different type of white blood cell or leukocyte. There are a number of different types of leukocytes. Here you see what seems to me is the immune system running in high gear with all systems go.